Hello again, and welcome. I'm glad you're here. Maybe today felt heavier than it should have, or maybe your mind is still wide awake when the rest of the world has gone quiet. Either way, this is your moment to let go. Let your breath slow. Let your shoulders soften. Let your thoughts drift, the way stars drift across a sky too large to measure. You don't need to fix anything. You don't need to chase answers. This time is yours. Tonight, we're setting out into one of the deepest mysteries the universe offers. Beyond the stars we can see, beyond the galaxies we can map, lies something stranger still. Invisible, immeasurable, and yet undeniable. Dark matter and dark energy. They shape the cosmos more than everything familiar, yet they hide just out of reach. They are not gaps in knowledge, but vast landscapes of mystery. Fields we can only explore through hints, shadows, and the bending of light. Over this journey, we'll wander through 100 quiet truths about this unseen universe, each one a step into the unknown, each one a chance to rest inside wonder. So, settle in. Tonight, the darkness glows. And while you're settling in, before your eyes grow too heavy, I'd love it if you gently tapped subscribe or pressed the little hype button YouTube recently added. It's a small click, but it helps keep these experiments and explorations orbiting out into the algorithm. You can also leave a comment telling me where you're listening from and what time it is in your corner of the night. It's oddly fascinating to see where people are drifting off with us, scattered across the world like stars across the galaxy. Now take a deep breath. Let your day drift away, and let's travel together into the quiet corners of the universe. The universe as we know it is only a thin veil stretched over something far deeper, stranger, and harder to see. When you look at the night sky, the points of light feel endless, a scatter of suns across immeasurable space. But all those stars, all the glowing galaxies, all the luminous dust add up to almost nothing. The great cosmic display is only the surface, less than 5% of what exists. The rest, the vast majority, remains invisible. It does not glow, it does not reflect, it does not shimmer, and yet it holds everything together and pushes everything apart. Scientists call this hidden portion dark matter and dark energy, but those are names more like placeholders than explanations. They are reminders that the universe is not what it seems, that the visible world is a fragment of a far larger whole. Dark matter is the unseen glue, a substance that outweighs the stars themselves, binding galaxies so tightly that they spin faster than light alone could permit. Dark energy is stranger still, not matter at all, but something in the fabric of space that drives it to expand, pushing galaxies farther and farther away. Together, they dominate the cosmos, shaping its past, its present, and its future. Imagine a stage where the actors are spotlit, vivid, and dramatic, while the machinery, scaffolding, and invisible wires that hold them up remain hidden in shadow. You watch the performance, you hear the lines, you see the movement, but you do not see what makes the illusion possible. The universe is like that. Stars, planets, nebulae, they are the actors. Dark matter and dark energy are the unseen machinery, the structure and tension without which the story would collapse. The first clues came not from what astronomers could see, but from what they couldn't explain. In the 1,930 seconds, Fritz Zwicky noticed galaxies in clusters moving too quickly, as if some invisible weight was pulling on them. Later, Vera Rubin's meticulous studies of galaxy rotation curves revealed the same strange truth. Stars on the edges of galaxies weren't slowing down as expected. They moved with nearly the same speed as stars near the center. That should have been impossible if gravity came only from visible matter. The conclusion was startling. Something unseen must be there, some hidden bulk holding galaxies together. And so the idea of dark matter solidified. It does not glow or burn, but its gravity is unmistakable. It outweighs ordinary matter about 5 to 1. You cannot see it directly, but you can trace its fingerprints in the way galaxies spin, in the bending of light as it passes through invisible concentrations of mass. In the structure of the universe, on the largest scales, dark matter is everywhere, forming halos around galaxies, stretching into vast filaments that weave the cosmic web. Without it, the stars would have drifted apart long ago, galaxies would not have formed, and the night sky would be empty. Dark energy was an even greater surprise. For decades, scientists thought the universe's expansion, discovered by Edwin Hubble, would gradually slow under the pull of gravity. But in the late 1990 seconds, two teams measuring distant supernovae found something shocking. Instead of slowing down, the expansion of the universe was speeding up. Galaxies were not just receding, they were accelerating away from one another. Some unknown force was pushing outward, a pressure not of matter but of space itself. They called it dark energy, though no one knows what it is. It makes up about 70% of the cosmos, an invisible tide that stretches reality farther apart with every passing moment. Together, dark matter and dark energy account for about 95% of everything. Ordinary matter, the atoms of stars, planets, and people, is barely a trace ingredient, a few percent scattered through an ocean of the unseen. When you hold a stone, when you feel the solidity of your own body, you are touching something rare. Most of the universe is not like this at all. Most of it is hidden, intangible, detectable only through its gravitational whispers and its effect on the shape of space. This raises questions so profound they border on the philosophical. What does it mean to live in a universe where nearly all of reality is invisible? How do we define the cosmos when we cannot see most of what it is? We exist in the light, but we are bound by the dark. The galaxies overhead are not freestanding islands of stars. They are ghost ships floating in vast, unseen seas, held together by matter that does not shine, carried along by an energy we do not understand. And so, when you look at the night sky, remember, the stars you see are only a sliver. The true universe is shadowed, but not empty. It is filled with forces and forms that remain beyond sight, shaping everything we know. This is the hidden universe, darker than imagination, stranger than fiction, and closer than breath. Even now, as you lie still, the Earth spins inside a halo of dark matter, the galaxy drifts through an invisible sea, and the whole universe stretches silently outward, guided by something we cannot yet name. The puzzle is not a void, but a presence vast enough to account for nearly all that exists. And in the chapters to come, we will wander through its quiet truths, tracing the outlines of what science has glimpsed, standing in the shadow of what it has yet to explain. For now, simply know this: the universe is mostly hidden, and that hiddenness is not emptiness but depth, a mystery that cradles every star and every life. Gravity is usually thought of as a familiar companion, a steady pull that keeps your feet pressed against the ground and holds the planets in their paths around the sun. For most of human history, gravity seemed simple, predictable, an invisible tether running through every object with mass. But when astronomers turned their eyes outward and measured how galaxies themselves spin, gravity began to whisper something stranger. It revealed not what we can see, but what must be there, even though it is invisible. Imagine a galaxy as a great wheel of stars, billions upon billions circling a common center. According to the laws of motion, the stars near the middle, closer to the dense cluster of light, should move swiftly, while stars near the edge, where less matter lies behind them, should slow down. It should look very much like planets in our solar system. Mercury racing fast near the sun, Neptune crawling on the outskirts. This expectation was clear, precise, and rooted in centuries of physics. But when the measurements came in, the universe did not agree. In the 1970 seconds, Vera Rubin, working night after night with her colleague Kent Ford, charted the rotation curves of spiral galaxies. They mapped the speed of stars at different distances from the galactic center, expecting to see the graceful downward slope predicted by Newton's law of gravity. Instead, what appeared was startling. The curve flattened. The stars at the edges moved just as quickly as those near the heart. They were whipping around with a speed that visible matter alone could not possibly explain. By every calculation, those outer stars should have flown off into the void, like sparks thrown from a wheel. Yet they held steady, bound by a gravity that seemed to come from nowhere. It was not an isolated anomaly. Rubin and others measured galaxy after galaxy, and each time the pattern held. The outer stars refused to slow down. The cosmic script of planetary motion, so well rehearsed in our solar system, was being defied on the grandest of stages. The only way to reconcile what the telescopes revealed was to accept that there must be more mass than we could see, far more. Something invisible was anchoring the stars, enveloping the galaxies in massive halos. The evidence was quiet but relentless. If gravity is the conversation between matter and motion, then the galaxies were speaking a language filled with hidden words. The visible stars, gas, and dust made up only a fraction of the story. The rest, the unseen bulk, was dark matter. Without it, the galaxies would unravel. With it, their graceful spinning made sense. Rubin herself spoke with wonder rather than finality. She did not claim to have solved the mystery, only to have traced its outline. Her careful graphs, lines drawn in ink and patience, showed the universe tugging at the corners of our knowledge. It was as though the night sky had leaned down and whispered, "There is more here than you think." Consider the scale of this revelation. In one step, the universe grew heavier and stranger. All the luminous matter, the suns blazing for billions of years, the nebulae glowing in pink and violet clouds, the great arms of spiral galaxies, turned out to be only the garnish on a much larger dish. The real mass, the true weight of the cosmos, lay hidden in shadow. It is a humbling thought that when you gaze at a galaxy, you are not seeing its whole body but only its shining skin. Beneath that skin, wrapped invisibly around it, lies a structure vaster than the eye can detect. Galaxies are not delicate pinwheels of light, but colossal ships buoyed up by unseen oceans. The stars ride their courses not because of the brilliance we admire, but because of the darkness we cannot see. The revelation of galaxy rotation curves reshaped astronomy in ways still unfolding. It was no longer enough to measure the glow of stars and gas. Astronomers had to infer what was present by its gravitational pull, mapping the invisible by the way it bends and binds. The cosmos became a place where absence was as important as presence, where the unseen shaped the fate of the seen. This is what gravity revealed. A universe where our senses catch only the surface, where the overwhelming majority of matter hides in shadow. It is a reminder that knowledge does not always arrive as a bright light in the sky. Sometimes it arrives as a quiet imbalance, a curve on a graph that refuses to dip, a whisper that tells us the story is larger than we thought. Even now, decades after Vera Rubin's careful observations, the mystery remains unsolved. We know the dark matter must be there, for without it galaxies would tear themselves apart, but we do not know what it is. Gravity has pointed the way, drawing the outline of a vast invisible presence, but the substance within that outline remains elusive. It is as though we have discovered the tracks of an animal never seen, traced its shadow, felt its weight in the soil, yet the creature itself stays hidden. And so, each time we look at the stars, we are also looking at their hidden companions, the dark halos that cradle them, the unseen gravity that lets them spin without scattering. The night sky is not only what shines, but what does not. It is not only the luminous, but the invisible scaffold that holds the luminous in place. This chapter of discovery is less about answers than about opening doors. The galaxies move too fast. Their stars defy expectation, and in that defiance, they point us toward a truth beyond light. What gravity reveals is that the universe is richer than it appears, bound together by something we cannot yet name, and waiting patiently for us to learn how to see. When we picture the universe, we often imagine it as a scatter of galaxies, drifting like lanterns in the dark. The distances are so immense, the space is so vast, that it can feel like everything is floating in isolation. But the truth, as uncovered by simulations and surveys, is that the cosmos is not random at all. Beneath the glittering points of light lies a hidden framework, a skeleton of invisible matter stretching from one horizon to the other. Galaxies are not scattered freely. They are threaded along filaments of something unseen, woven into a web so enormous it defies imagination. This is the cosmic scaffolding, built not of atoms or stars, but of dark matter. The evidence comes not from direct sight, for dark matter remains invisible, but from the patterns its gravity enforces. In computer simulations of the early universe, scientists seeded tiny fluctuations into an expanding cloud of energy and matter. With time, under the patient tug of gravity, these fluctuations grew, collapsing into strands and knots. The result was not a smooth distribution, but a vast network resembling a spider's web, with long filaments intersecting at dense nodes. It was within these intersections that galaxies would ignite. The luminous structures we see through telescopes are only the glowing tracery atop this deeper, invisible framework. This discovery changed how we think about the universe's architecture. Rather than a scattered sea of galaxies, the cosmos reveals itself as a tapestry. Galaxies cling to filaments like beads on threads, while enormous voids stretch between them, silent expanses almost empty of stars. If you could step back far enough, farther than any eye or instrument can travel, you would see something astonishing. The entire universe patterned like lace, luminous galaxies strung along invisible highways of dark matter, the whole of reality shaped by something it cannot show. It is a paradox, both humbling and beautiful. We see only the light, yet it is the darkness that gives the light its place. Stars and galaxies are like frost forming on unseen branches, patterns made possible by what lies beneath. Without dark matter, the filaments would not exist, the clusters would not coalesce, and the galaxies themselves would not take shape. The scaffolding of the cosmos is not decoration. It is foundation. It is the hidden geometry on which the universe has been built. Observations of deep space support what simulations predict. When astronomers map galaxies across billions of light years, they do not find a random spray. They see chains, clusters, filaments stretching like bridges, and immense empty regions in between. These cosmic voids are as striking as the filaments themselves, regions so vast and dark that 1,000 Milky Ways could pass through without touching a single star. And yet even these voids are defined by dark matter, for it is the invisible weight of matter elsewhere that pushes them open, carving hollows where light dares not linger. Gravitational lensing provides another window into this hidden scaffolding. Light from distant galaxies bends as it passes massive objects, curving around invisible concentrations of dark matter. By tracing these distortions, astronomers can map the unseen, sketching the filaments of the cosmic web not by their glow, but by their pull. The results confirm the picture. A universe bound and stretched by an invisible framework, the stars mere dust motes caught in its unseen strands. To imagine this is to change one's sense of scale. Each galaxy, each island of light, is only a small ornament in a network stretching hundreds of millions of light years. We are part of a single thread, our Milky Way resting inside a dark matter filament that extends far beyond sight, linking us to other clusters and superclusters across unfathomable gulfs. The night sky, for all its brilliance, is the merest surface shimmer of this deeper order. There is something quietly comforting in this vision. Though space feels empty, though stars appear scattered, the universe is not without structure. It is bound together by hidden connections, filaments stretching across the dark. We are not adrift in chaos, but embedded in a pattern, woven into a cosmic web. It is a reminder that even in the absence of light, there is form and order, a hidden architecture that holds us in place. Dark matter does not announce itself. It does not shine. It does not flare. It does not burn. Yet its silent presence has arranged the universe into the shape we know. The galaxies are only tracers of its design, the luminous embroidery on a fabric far larger and darker than we can see. In that sense, the cosmic scaffolding is not just structure. It is story. It tells of beginnings, of growth, of a universe drawn into shape by what it cannot reveal. And so when you look at the stars, remember that they are not floating free. They are bound into place by threads of the unseen, stitched into a cosmic tapestry of extraordinary scale. The light you admire is only the outline, the faint tracing on an invisible frame. The true universe is not only what shines, but what holds the shining together. It is a web spun from the dark, a scaffolding vast enough to cradle all the galaxies and quiet enough to let them glow. Light, for all its speed and clarity, is not immune to gravity. It moves in straight lines only until it crosses paths with something massive, something with enough weight to bend the fabric of space itself. Then light curves, tracing arcs that should not exist, making distant objects appear stretched, duplicated, or magnified. To the human eye, this bending can look like distortion. To astronomers, it is a gift. For when light bends where nothing visible is there, it reveals the invisible hand of dark matter. This phenomenon is called gravitational lensing, and it has become one of the most powerful ways we know the unseen exists. The principle is simple but profound. Mass warps space, and space guides light. Even if the mass cannot be seen, its presence is betrayed by the way it alters the path of photons traveling across billions of light years. A galaxy, a cluster, even a cloud of dark matter itself can act like a lens, reshaping the light from objects behind it into arcs and rings, ghostly smears across the sky. In this way, the dark writes its signature in the language of light. There are gentle versions of lensing where the effect is subtle, stretching galaxies into faint ovals, a quiet whisper of distortion. By collecting these small signals across wide fields of sky, astronomers can map how dark matter is spread on cosmic scales. It is painstaking work, like tracing the outline of wind by watching how it moves blades of grass. And then there are dramatic versions, strong lensing, where entire galaxies are split into multiple images or bent into nearly perfect circles of light called Einstein rings. These spectacles are rare but striking, proof that gravity can sculpt light itself into new forms. The most famous example of gravitational lensing as a revelation of dark matter is found in the Bullet Cluster. Here, two massive galaxy clusters collided, their luminous matter, stars, gas, plasma, slamming together in a fiery, visible crash. But the gravitational lensing told another story. The bulk of the mass did not remain with the glowing gas. It passed through the collision almost untouched, invisible but still detectable by the way it bent background light. The lensing maps showed the invisible mass separated from the visible matter, offset like two shadows that refused to match the bodies casting them. This was the smoking gun. It proved that dark matter is not just a trick of gravity or a flaw in our equations. It moves independently, interacting very little with ordinary matter except through the pull of gravity. The Bullet Cluster laid bare the divide between what shines and what truly weighs. In one cosmic collision, the universe had sketched its secrets in unmistakable contrast. Beyond the Bullet Cluster, other observations deepen the story. In surveys of thousands of galaxies, faint lensing effects weave together a picture of the cosmic web, tracing filaments of dark matter stretching across billions of light years. These maps confirm what simulations predicted. Galaxies cling to invisible scaffolds, their shapes distorted in ways that reveal the presence of structures we cannot otherwise see. Each lensing event is like a fingerprint, unique yet part of a larger pattern, building evidence for the unseen framework of the universe. There is wonder, too, in how lensing allows us to see farther than we otherwise could. Massive clusters act like natural telescopes, magnifying galaxies from the earliest ages of the cosmos. Some of the most ancient and distant galaxies known were glimpsed because dark matter's gravity bent their light toward us. In this way, the invisible not only hides, but also reveals, offering windows into times and places that would otherwise be forever out of reach. The elegance of gravitational lensing lies in its duality. It is at once a distortion and a revelation. It bends what we see, yet through that bending, it unveils what we cannot see directly. The arcs and smears in the sky are not mistakes but messages, written by a cosmos that hides most of its substance in shadow. Each warped galaxy, each stretched arc of light, is a quiet declaration. There is more here than meets the eye. And so, as light travels across the dark seas of space, it carries with it the outlines of the unseen. It curves where invisible mountains of mass loom. It arcs around halos of darkness. It whispers to us in distortions and duplications. By listening carefully, by charting every subtle bend, we are learning the shape of the hidden universe. The stars give us brightness, but it is gravity, bending light into unexpected paths, that gives us truth. In the end, gravitational lensing is not just a trick of physics, but a reminder of how reality hides itself in plain sight. The night sky appears serene and orderly, but behind that calm surface lies a restless architecture of mass and motion. Light, bent by the unseen, lets us glimpse that deeper order. It is the universe tipping its hand, allowing us, for just a moment, to see the weight of the dark. For decades, scientists have known dark matter must exist. The galaxies spin too quickly. The universe holds together too firmly for ordinary matter alone to explain. Yet knowing it is there and knowing what it is are two very different things. The hunt for its particles has become one of the most ambitious quests in modern science, an effort that has led us into mountains, deserts, and deep underground caverns where enormous detectors wait in silence, hoping to catch the faintest whisper from the dark. The leading idea for many years has been the WIMP, short for weakly interacting massive particle. The theory suggests that dark matter might be made of particles heavier than protons, but interacting so rarely with normal matter that they pass through entire planets without a trace. WIMPs became a favored candidate because they fit neatly into extensions of the standard model of physics, offering not just an explanation for dark matter, but a way to tie together other puzzles of particle physics. If they exist, then once in a great while, one might bump into the nucleus of an atom, leaving behind a tiny flash of energy that could be measured. That faint possibility is enough to fuel detectors the size of houses. In recent years, another idea has gained traction: the Axion. Unlike WIMPs, Axions would be almost unimaginably light, so ghostly that billions could pass through every square centimeter of space without anyone noticing. They were originally proposed not to solve the dark matter problem, but to explain a quirk in the behavior of quarks, one of the building blocks of atoms. Yet in their strangeness, Axions turned out to be perfect candidates for dark matter. If they exist, they could form vast waves, like invisible tides sweeping through galaxies. Scientists have built experiments using ultra-sensitive electromagnetic detectors, hoping to catch the faint hum of axions resonating in magnetic fields. There are other possibilities too, like sterile neutrinos, cousins of the neutrinos we already know, but even more elusive. Normal neutrinos are already difficult to detect. Trillions pass through your body every second without leaving a trace. A sterile version, interacting only through gravity, would be nearly impossible to capture. Yet their existence would elegantly explain certain cosmic puzzles, and so they remain on the table, ghostly suspects in this cosmic investigation. The search for these particles has driven some of the most remarkable experiments on Earth. To avoid the interference of cosmic rays and background noise, scientists have buried massive detectors deep underground, shielded by rock. In these chambers, giant tanks filled with ultra-pure liquid xenon or argon stand waiting. If a dark matter particle collides with one of the atoms inside, it should produce a flash of light and a ripple of charge, a signal so faint it would be drowned out anywhere else. These experiments are so sensitive they can detect the faint glow of a single photon, yet years pass with silence, the detectors recording nothing but background noise. Still, the silence itself is information. Each null result tells scientists what dark matter is not, narrowing the possibilities, pushing theories into new directions. It is like searching a vast mansion in darkness, room by room, knowing the presence of something unseen, but finding each chamber empty. The emptiness sharpens the search, guiding the next step. Meanwhile, at the Large Hadron Collider, particles are smashed together at energies meant to mimic the earliest moments of the universe. If dark matter particles can be created, they would appear not as tracks in the detectors, but as missing energy, as something slipping away unseen. To date, the colliders too have been silent on the matter. Yet each run, each burst of data, adds another piece to the puzzle. The quiet persistence of this search has a kind of beauty. Scientists build instruments of exquisite sensitivity, lower them into caverns, and wait. They are listening for whispers in a universe filled with noise, hoping to catch a fleeting interaction from a particle that passes through entire planets as if they were empty space. The patience is immense. The faith is profound. For decades, the detectors have been listening, and still they listen, because the mystery demands it. It is humbling to think that the nature of most of the universe may depend on particles we have never touched, never seen, never even proven exist. And yet this is how science often works, through persistence in the face of silence, through narrowing the unknown with every unanswered question. The search for dark matter particles is not only about discovery, it is also about endurance, about holding fast to curiosity when the dark does not yet yield. Perhaps someday, a faint signal will appear, a tiny burst of light in a xenon tank, a faint resonance in a magnetic field, a shadow of missing energy in a collider's data. Or perhaps, the answer lies in a place no one has thought to look. Until then, the experiments continue, vast machines humming in the dark, listening for the invisible heartbeat of the universe. When scientists first realized galaxies spun too fast for the matter they contained, the idea of an invisible particle was not the only explanation considered. Before WIMPs, Axions, and sterile neutrinos took center stage, astronomers turned to something more familiar. Perhaps the missing mass was not exotic at all, but simply hard to see. Ordinary matter hiding in plain sight. Could the universe be filled with faint stars, wandering planets, or collapsed remnants of dead suns? These objects were given a collective name, MACHOs, short for massive compact halo objects. The idea was simple enough. If the outskirts of galaxies seemed too heavy, perhaps they were padded with swarms of dim objects. Brown dwarfs, too small to shine like stars. Rogue planets, cast adrift in the darkness. White dwarfs, neutron stars, or even black holes, each invisible, except when they revealed themselves through a flare of gravity. Our own galaxy, the Milky Way, is surrounded by a vast halo. Could it be that this halo is filled not with some strange, unseen particle, but with ordinary objects too faint to notice from afar? To test this, astronomers turn to a trick of nature, gravitational microlensing. When a compact object passes in front of a distant star, its gravity bends the star's light ever so slightly, making it brighten and dim in a telltale curve. By monitoring millions of stars in the Magellanic Clouds and the galactic bulge, surveys like MACHO, Eros, and OGLE searched for these flickers. Each detection would reveal a hidden body, a candidate for the dark matter in the halo. They did find some. A few dim stars, a handful of events hinting at objects the mass of planets or brown dwarfs. But the numbers fell short. To explain the full weight of the galaxy's missing matter, there would have needed to be hundreds of times more of these events. The surveys suggested MACHOs exist, but not in the abundance required to make up the invisible bulk. The halo, it seemed, was not crowded with faint suns or wandering planets. Something else must be carrying the weight. Still, the idea has not fully vanished. Primordial black holes remain an intriguing possibility. Unlike the black holes formed from dying stars, primordial black holes would have been born in the earliest moments after the Big Bang, forged from fluctuations in the density of matter itself. They could range in size from microscopic specks to giants heavier than stars, hiding silently in the dark. If enough of them existed, they might account for dark matter. Evidence for this remains elusive. Some observations of gravitational waves, ripples in spacetime from colliding black holes, sparked speculation that the merging black holes detected by LIGO might be primordial. Yet careful study suggests otherwise, and the abundance needed to explain all dark matter does not align neatly with the data. Microlensing surveys again place limits. Too many primordial black holes would have revealed themselves in flickers of distant starlight, and they have not. And yet, small gaps remain, ranges of mass where the possibility cannot be fully excluded. The idea of hidden planets, faint stars, and black holes as dark matter is appealing because it asks us to imagine a universe filled not with the exotic but with the familiar. It would mean the darkness is not made of some unknown substance, but of ordinary matter lurking where our instruments cannot yet reach. But the evidence resists this comforting simplicity. The universe seems to demand something stranger, something beyond the particles we know. And yet the story of MACHOs and black holes is important because it reminds us how science moves, by testing every possibility, ruling out the likely, and leaving behind what fits. Even when ideas fade, they leave traces, shaping the next questions, refining the search. The dark matter mystery is not solved by discarding, but by narrowing. MACHOs may not be the answer, but in their failure they guide us closer to what might be. Imagine for a moment, though, what it would mean if the halo of our galaxy were filled with countless invisible companions, worlds drifting without suns, ancient black holes sliding silently through the void, stars so dim they glow only faintly in infrared. It is a haunting vision, a galaxy crowded with ghosts. Even if they cannot explain the universe's missing mass, such objects still exist, reminders that the dark is never empty, only waiting. The search continues, shifting toward particles more exotic than planets, more elusive than faint stars. But the chapter of MACHOs and black holes lingers in the background, a reminder that the unseen could be closer than we think. Perhaps not the whole answer, but part of the tapestry. Perhaps not the scaffolding itself, but shadows hanging from its threads. In the silence of the cosmic halo, possibilities remain, flickering faintly like stars half swallowed by night. At the dawn of time, long before galaxies had formed or stars had lit their fires, the universe was filled with a glowing fog. It was hot, dense, and nearly uniform, a sea of particles and radiation so tightly coupled that light could not travel freely. Every photon scattered endlessly off electrons, trapped in a brilliant haze that stretched in all directions. For nearly 400,000 years after the Big Bang, the universe was like this, opaque, restless, pulsing with subtle ripples of density. And it is within those ripples, frozen into the fabric of ancient light, that the fingerprints of dark matter are found. When the universe cooled enough for electrons to bind with protons, atoms finally formed. For the first time, photons could stream freely across space, carrying with them a record of the conditions in that moment. This radiation still bathes the universe today, stretched by expansion into a faint afterglow known as the cosmic microwave background. Though it looks almost perfectly smooth, it is not. Tiny variations in temperature, just a few millionths of a degree, map the seeds of cosmic structure. These fluctuations are the imprints of a young universe, beginning to decide where galaxies, clusters, and voids would someday be. The cosmic microwave background, or CMB, is not just a relic, it is a message. Its faint patterns reveal what the universe was made of in its earliest days. If the cosmos had been composed only of ordinary matter and radiation, the ripples in the CMB would look very different. Ordinary matter interacts with light. It pushes back, oscillates, resists collapse. But dark matter, indifferent to photons, provided something else entirely: a silent gravitational anchor. It allowed overdense regions to deepen without scattering light, to grow while the visible matter danced restlessly with radiation. Without dark matter, the patterns etched into the CMB would not match what we see today. The temperature map of the CMB, first captured in exquisite detail by the COBE satellite and later by WMAP and Planck, shows peaks and valleys that are more than random noise. They are harmonics, the echoes of sound waves that rippled through the plasma of the early universe. Just as the tone of a drum depends on the shape of its skin, the exact distribution of these peaks depends on the ingredients of the cosmos. By comparing theory to observation, scientists discovered a striking truth. The universe of the past already carried the weight of dark matter. Its gravity was essential to sculpting the precise pattern we now see stretched across the sky. This is one of the most compelling proofs that dark matter is real. It shows that the missing mass was not a late addition, not a quirk of galaxies alone, but a presence from the very beginning. In the first few 100,000 years, when everything was still glowing, dark matter was already there, invisible but decisive, guiding the evolution of structure. The CMB tells us that dark matter makes up about a quarter of the total contents of the universe, while ordinary matter is only a fraction of that. Without dark matter, the universe would look utterly different today. It is a strange thought that the afterglow of the Big Bang carries within it a story written not by light, but by what light cannot touch. The photons that reach our detectors today have been traveling for over 13 billion years, slipping past galaxies, weaving through voids, arriving as faint microwaves. Yet their tiny fluctuations tell us of the silent hand of the dark, of the hidden scaffolding that pulled matter together even before the first star was born. In this way, the CMB becomes both a relic and a map. It preserves the conditions of a cosmos still in its infancy, but it also projects forward, showing why galaxies formed where they did, why clusters sit at the junctions of filaments, why the universe looks the way it does now. Every arc and ripple in that ancient light is an echo of dark matter's gravity, a subtle reminder that the cosmos has always been more shadow than shine. To gaze at the CMB is to look at a photograph of the universe as a child. The faint modeling, the delicate anisotropies, are like freckles across its young face. Hidden in those freckles is a message that even in its earliest days, the universe carried within it more than we could see. And in that unseen abundance lay the blueprint of everything that would come. The story of dark matter is often told through galaxies that spin too fast or clusters that weigh too much. But the cosmic microwave background reaches further back, to a time when there were no galaxies at all. It tells us that the invisible was always there, woven into the universe from the very start, shaping its growth in ways that light alone never could. The universe began in brilliance, but it was the darkness that gave that brilliance form. The effort to chart the unseen begins with a paradox. How do you map something that does not emit light, cannot be photographed, and refuses to reveal itself to any direct observation? The answer lies not in looking for the invisible itself, but in tracing its influence on what we can see. Over the past few decades, astronomers have built surveys of staggering scale, compiling catalogs of millions of galaxies, mapping the faint glow of ancient radiation, and measuring the delicate distortions of starlight as it passes through the cosmos. Each of these efforts is a kind of cartography, a way of sketching the outlines of the unseen. One of the most ambitious of these is the Sloan Digital Sky Survey, known as SDSS. Beginning in the year 2000, It set out with a simple but audacious goal: to create the most detailed three-dimensional map of the universe ever attempted. With a dedicated telescope in New Mexico, it has scanned wide swaths of the sky, recording not just images of galaxies but also their spectra, which reveal distances through the redshifts of their light. Piece by piece, it has built a map of cosmic structure, a web of filaments and voids stretching across billions of light years. In this grand survey, galaxies appear not as isolated points, but as tracers of something larger. They cling to threads and clusters, marking the skeleton of dark matter beneath them. The pattern revealed by SDSS is unmistakable. Instead of a random scatter, galaxies align into walls and chains, separated by enormous empty regions. The scale is breathtaking, with structures so vast they stretch hundreds of millions of light years. This cosmic web matches the predictions of simulations where dark matter forms the scaffolding of the universe, guiding galaxies into place. It is as though the visible cosmos is draped across an invisible lattice, every star and spiral a bead strung along threads of darkness. While galaxy surveys chart the large-scale structure, other instruments have looked deeper into time. The Planck satellite, launched in 2009, measured the cosmic microwave background with exquisite precision, capturing tiny variations in the ancient light from just after the Big Bang. These fluctuations encode not only the seeds of galaxies, but also the balance of matter and energy in the early universe. By analyzing the fine details of the CMB's pattern, scientists have pinned down how much of the cosmos must be dark matter. Planck's maps show the universe as it was nearly 14 billion years ago, a baby picture that reveals, with stunning clarity, the presence of the invisible even then. And then there is the technique of weak gravitational lensing, which offers yet another way of mapping the unseen. Here, the effect is subtle. Instead of dramatic arcs and rings, the light from countless distant galaxies is stretched ever so slightly by the gravity of intervening mass. By measuring these distortions across huge swaths of the sky, astronomers can reconstruct where the hidden mass lies. It is like watching how a breeze bends the grass in a field, and from that, inferring the shape of the wind. Surveys using weak lensing, such as the Dark Energy Survey and others, have produced maps where the invisible dark matter is traced in ghostly blue, showing filaments and knots that align with but outweigh the galaxies themselves. Each of these methods, in its own way, adds layers to the map. SDSS gives us the three-dimensional structure of galaxy distribution. Planck provides the ancient blueprint, the initial conditions from which structure grew. Weak lensing reveals the distribution of mass itself, luminous or not, letting us see the web directly in gravitational silhouette. Together, they form a composite picture of the cosmos, not just the shining galaxies, but the dark skeleton on which they hang. To imagine this map is to imagine the universe as a vast web, glowing faintly in the night, with clusters of galaxies shining at the intersections, and long filaments stretching between them like bridges of shadow. We are inside one of those filaments, our own Milky Way, part of a thread that spans far beyond what our eyes can see. It is a vision of belonging, of being woven into a cosmic structure that is at once invisible and immense. What is remarkable is not only that we have glimpsed this structure, but that we have done so without ever seeing dark matter itself. Its presence is inferred, its map drawn from distortions, distributions, and echoes. It is a cartography of absence, a charting of what cannot be touched, built from the whispers of light and gravity. And yet it is as real as any map of rivers and mountains, as enduring as any geography. To map the invisible is to accept that the universe speaks in indirect signs. Light bends, galaxies cluster, radiation flickers with ancient patterns. From these traces, we reconstruct the unseen, filling in the canvas with what must be there. It is a work of patience, of imagination, and of deep trust in the language of physics. The surveys and satellites are our tools, but the real map is written in the fabric of space-time itself. And so, The universe takes shape, not only through what shines, but through what does not. Our maps now extend across billions of light years, showing us the dark scaffolding of reality with increasing clarity. Each survey, each observation, is a lantern held up against the vastness, revealing more of the hidden web. Though the darkness itself never glows, its structure has been traced, and in those tracings lies a portrait of the universe both more mysterious and more beautiful than we once imagined. Galaxy clusters are the grand assemblies of the cosmos, the largest structures held together by gravity. Where galaxies on their own already seem immense, a cluster gathers hundreds or even thousands of them into a single community, bound across tens of millions of light years. To look at a cluster is to see a swarm of galaxies, each shining with billions of stars, yet all orbiting one another like bees in a hive. And it is within these immense congregations that the strongest evidence for dark matter is found, because the gravity required to hold them together is far greater than what the visible stars and gas can provide. The first hints came in the 1930 seconds, when Fritz Zwicky observed the Coma cluster. He measured the speeds of galaxies within it, and found they were moving far too fast to be bound by the mass of the luminous galaxies alone. By the normal rules of gravity, the cluster should have flown apart, its galaxies scattering into the void, but it held together, tight and coherent. Zwicky proposed that there must be unseen matter providing the extra pull, an invisible bulk outweighing the luminous galaxies many times over. He called it Dunkel Materie, dark matter. At the time, the idea seemed speculative, even radical. But the puzzle lingered. Decades later, with more refined instruments, the evidence grew undeniable. When astronomers measured the hot gas-filling clusters, the vast clouds of plasma glowing in X-rays, they found the gas alone contained more mass than all the stars combined. Yet even this was not enough. To keep galaxies moving at the observed speeds, to keep the clusters from flying apart, still more mass was needed. Something unseen, something not shining, had to account for the lion's share of the weight. Today, the consensus is clear. Dark matter dominates galaxy clusters. Stars contribute only a few % of the mass, gas adds a larger share, but the hidden matter makes up the majority. Without it, the entire structure would disintegrate. With it, clusters persist as some of the most spectacular and enduring features in the universe. Gravitational lensing adds another layer of proof. Light from galaxies lying behind a cluster is bent and magnified by the cluster's immense gravity. And by studying the distortions, astronomers can map how the mass is distributed. Time and again, these maps reveal concentrations of matter far greater than what the luminous galaxies and gas account for. The arcs and smeared images of distant galaxies, stretched around the edges of clusters, are like signatures of the invisible. They show us directly that most of the mass lies hidden, spread out in halos and knots that cradle the galaxies we can see. One of the most famous cases is the Bullet cluster, where two galaxy clusters collided. The luminous gas, heated to extreme temperatures, slowed and lagged behind, glowing fiercely in X-rays. But the gravitational lensing maps revealed that the bulk of the mass had passed straight through, hardly interacting at all. The galaxies themselves, and the dark matter enveloping them, moved on, while the ordinary matter, the gas, remained behind. It was dramatic, visual evidence that dark matter is not just a tweak to our theories, but a real substance, distinct from ordinary matter, shaping the universe at the largest scales. To stand back and imagine a galaxy cluster is to picture not just a crowd of galaxies, but a hidden mountain of gravity, a vast well that holds them in place. The luminous matter, brilliant as it is only a tracer, floating on an invisible sea. The cluster's true bulk, its real skeleton, is something we cannot touch or see, but which reveals itself in every orbit, every bent beam of light, every stubborn refusal to scatter apart. There is something both haunting and comforting in this. Haunting, because it tells us that even the brightest structures in the universe are mostly shadow, bound by a presence we do not understand. Comforting, because it means the cosmos is not chaotic, but deeply ordered, its largest forms held together by an invisible glue. We are not witnessing galaxies adrift, but galaxies anchored, clustered in patterns carved by the unseen. In clusters, the argument for dark matter ceases to be subtle. It is not hidden in small anomalies or delicate imbalances, but writ large across the cosmos. The evidence is towering, undeniable, vast enough to bind hundreds of galaxies into a single whole. And so these clusters, glowing islands in the ocean of space, stand as monuments to the invisible, proof that the darkness outweighs the light. In the vast stillness of space, most collisions unfold in silence. Galaxies drift into one another over billions of years, their stars rarely touching, their motions patient and slow. But in the case of the Bullet Cluster, something extraordinary happened. Two massive galaxy clusters collided head-on, leaving behind a cosmic crime scene that revealed one of the clearest pieces of evidence for dark matter. It is as if the universe itself staged an experiment, and in the aftermath, the truth was written across the sky. A galaxy cluster is already immense, containing hundreds of galaxies, clouds of hot gas, and a hidden halo of unseen mass. When two such giants collide, the galaxies within mostly pass through one another like ships on a foggy night, too small compared to the vast spaces between them to interact. But the gas is different. Clouds of plasma, hotter than the cores of stars, slam together with such force that they slow and pile up, radiating X-rays that we can detect with space telescopes. In the Bullet Cluster, this hot gas is what gives the system its name. A bright, bullet-shaped plume carved by the smaller cluster as it tore through the larger one. What makes the Bullet Cluster remarkable is not just the spectacle of the collision, but the way matter split from light. When astronomers mapped the visible galaxies and the glowing X-ray gas, they found much of the ordinary matter lagging behind, caught in the friction of impact. But when they turned to gravitational lensing, measuring how the cluster's mass bent the light of galaxies lying behind it, the lensing maps told a different story. The majority of the mass was not where the hot gas glowed brightest. It was offset, aligned with the galaxies themselves, as though an invisible component had passed straight through the collision unaffected. This invisible component is dark matter. Unlike the gas, it does not interact through friction or electromagnetic forces. Unlike the stars, it does not shine. It responds only to gravity, sliding through the chaos untouched, holding its alignment with the galaxies while the ordinary matter falls behind. The result is a cosmic separation. Luminous matter on one side, gravitational mass on the other. For decades, skeptics of dark matter argued that perhaps the strange motions of galaxies could be explained by modifications to the laws of gravity themselves. Perhaps no unseen matter was required at all. But the Bullet Cluster stands as a rebuttal. Modified gravity alone cannot explain why the gravitational mass in the system is not where the visible matter is. Only an additional, invisible form of matter, dark matter, fits the evidence. The cluster became a kind of smoking gun, proof that the unseen is not merely a theoretical crutch, but a real, independent component of the cosmos. To look at the Bullet Cluster is to see layers of the universe peeled apart. In optical light, you see galaxies glimmering like jewels. In X-rays, you see the hot gas, piled and shocked into brilliant arcs. In gravitational lensing maps, you see the ghostly silhouettes of invisible halos, heavier and larger than everything else combined. Together, they form a composite picture of the cosmos divided. What shines, what glows, and what weighs. There is something haunting in this revelation. In most cases, the hidden and the visible remain entwined. Galaxies bound to their dark matter halos, their motions betraying what lies beneath. But here, the collision tore them apart, making the invisible visible by its very independence. Dark matter passed through unscathed, refusing to reveal itself directly, yet leaving its gravitational fingerprints unmistakably behind. The bullet cluster is not the only example. Other cluster collisions, like the so-called baby bullet and the train wreck cluster, show similar separations, each reinforcing the case. But the bullet cluster remains the most iconic, its clean geometry and striking appearance, making it a symbol of the dark matter mystery. It is the universe speaking in the starkest terms it can. There is more here than meets the eye, and it moves by its own rules. In that way, the bullet cluster is more than an object of study. It is a reminder of how the cosmos hides and reveals itself. Sometimes light is not enough. Sometimes the truth lies in gravity's pull, in the way it bends light and anchors galaxies, even when no matter glows. To contemplate this system is to glimpse the strange duality of existence. A universe where what we see is only part of the story, and where the greater part passes through silently, untouched, invisible, but undeniably real. The bullet cluster, frozen in the aftermath of collision, tells us that dark matter is not a trick of perspective, not an illusion in our mathematics. It is a substance with its own destiny, woven into the fabric of the cosmos from the very beginning. It is the shadow body of the universe, revealed most clearly not in stillness but in impact, when the visible and the invisible are forced apart. And so this one cluster, 3.8 billion light-years away, stands as a cosmic witness, its fractured light whispering the truth. The darkness is real, and it outweighs the light. Every galaxy you can see in the night sky, from the delicate spirals to the bloated ellipticals, is thought to be wrapped in something it cannot show. Around each disk of stars, each glowing halo of gas, lies a far greater envelope of invisible matter, an immense cocoon that does not shine, but whose gravity holds everything together. These are dark matter halos, the silent anchors of galaxies, and without them, the universe would look nothing like it does now. The evidence comes first from the way galaxies spin. The stars on the outskirts, far from the bright centers, move too quickly to be bound by the visible mass alone. If only the stars, gas, and dust contributed to gravity, those outer stars should be flung away into intergalactic space, yet they remain in orbit, circling their galaxies as though tethered by an unseen hand. The conclusion is inescapable. A vast halo of invisible matter surrounds each galaxy, outweighing the luminous material by a factor of 5 or more. This hidden sphere stretches far beyond the edges of the visible disk, enveloping the galaxy in a structure much larger than what the eye can see. The Milky Way is no exception. Our home galaxy, with its spiral arms and glowing core, is believed to be encased in a dark halo that extends hundreds of thousands of light-years in every direction. We cannot see it, but we feel its presence in the motions of stars, in the paths of satellite galaxies, in the way the Magellanic Clouds dance around us, pulled by more gravity than the Milky Way's visible mass can provide. Even the faint streams of stars, remnants of dwarf galaxies long since torn apart, trace the invisible contours of this halo, outlining a skeleton of darkness on which our galaxy is built. Simulations of cosmic structure show why these halos are essential. Without dark matter, galaxies would not have formed at all. In the early universe, ordinary matter was too entangled with radiation to clump efficiently. It was the dark matter, immune to light, that began to collapse first, forming halos that acted as cradles. Into these gravitational wells, gas eventually fell, cooled, and ignited into stars. Every galaxy, from the smallest dwarf to the largest giant, owes its existence to the dark halos that preceded them. They are not afterthoughts, but the very conditions that made galaxies possible. Observations confirm this at many scales. Satellite galaxies cluster around larger ones in patterns determined by the mass of halos. Gravitational lensing reveals halos as ghostly fingerprints, bending light around galaxies in ways that betray far more mass than what glows. The halos extend so far beyond the visible edges that if you could see them, galaxies would not appear as delicate spirals or neat ellipses, but as glowing seeds suspended inside enormous faint spheres. The shapes we admire are only the luminous hearts of far vaster, darker bodies. It is strange to realize that what we consider a galaxy is, in truth, incomplete. When you look at Andromeda, the faint smudge in the sky, you are seeing only its luminous skin. Its halo, though invisible, stretches far wider, overlapping even with the Milky Way's halo across the gap of intergalactic space. The two galaxies, still millions of years from collision, are already touching in their dark outskirts. Our future union is not only written in the motion of stars, but in the embrace of halos that already intertwine. There is a quiet poetry in the thought that galaxies are held together by what they cannot show. Stars and gas would drift apart without this hidden gravity. Spirals would unravel. Clusters would collapse. Instead, the halos bind them, allowing beauty to take form, sustaining order across billions of years. The luminous is only a tracer, the visible echo of a far greater structure. It is not the light that defines a galaxy's shape, but the darkness beneath it. And yet, for all we know about halos, their true nature remains mysterious. What fills them? WIMPs, Axions, sterile neutrinos, or something stranger still? The halos are both the most certain evidence of dark matter and the deepest reminders of how little we understand. We can measure their mass, trace their extent, even map their influence, but the substance itself remains hidden. They are both foundations and enigmas, silent containers of the universe's weight. When you look up at the night sky, remember that every pinprick of light belongs to a galaxy balanced inside an invisible sphere. The stars you see are not free-floating, but suspended in the gravity of halos that stretch farther than vision can reach. Our own world circles inside one now, the Earth itself moving along paths shaped by a vast invisible body we cannot touch. The galaxy's glow is only the surface of its reality. The rest lies in shadow, immense, enduring, and unseen. Stars seem eternal, fixed in the night like beacons that have always been there. Yet each one is the product of a delicate process, born in clouds of gas that collapse under their own weight until nuclear fire ignites at their cores. The surprising truth is that this process, the very act of star formation, depends not only on gas and gravity, but also on the invisible presence of dark matter. Without it, the cosmos would be a far dimmer place, perhaps almost entirely dark, with few stars to light the void. In the earliest days after the Big Bang, the universe was filled with a nearly uniform haze of hydrogen and helium. Gravity began to tug at small fluctuations in density, drawing matter together into clumps. But the ordinary matter, coupled tightly to radiation, resisted collapse. It was restless, scattering photons and bouncing in oscillations. If the universe had been made only of atoms and light, those ripples might never have grown enough to form galaxies at all. The cosmos would have expanded into emptiness, too smooth to seed the brilliance of stars. Dark matter changed that. Immune to light, it began to clump earlier, collapsing into invisible halos long before ordinary matter could follow. These halos created deep wells of gravity, silent basins where gas could eventually collect once it cooled enough to decouple from radiation. The dark matter provided the scaffolding, the framework on which the first galaxies would be built. Without it, the starry architecture of the universe would not exist. Simulations of cosmic evolution confirm this picture. When astronomers model the universe with only ordinary matter, structure fails to form. Add dark matter, and suddenly, the cosmic web emerges, filaments and halos growing across billions of years, each one cradling gas that cools into stars. The difference is stark. In one case, emptiness. In the other, the universe we recognize, alive with galaxies and light. The presence of dark matter is not a small adjustment. It is the deciding factor between a barren cosmos and one filled with stars. Even today, the role of dark matter in shaping star formation continues. The halos surrounding galaxies act as reservoirs, their gravity drawing in gas from intergalactic space. Streams of hydrogen fall along filaments, feeding the growth of galaxies, sustaining star formation across cosmic time. In galaxies with massive halos, the inflow of gas is steady, supporting generations of stars. In those with small or stripped halos, star formation falters, the gas too easily blown away by supernovae or cosmic winds. Observations of dwarf galaxies illustrate this dependence. The faintest dwarfs, with weak halos, often struggle to form stars at all. Many appear as dark matter-dominated systems with only a sprinkling of luminous matter, their halos unable to hold onto enough gas to build more. In contrast, massive halos, like that of the Milky Way, cradle not just billions of stars, but also the conditions to form new ones, recycling gas through supernova explosions and accretion flows. It is the halo that determines the fate of the galaxy's light. The interplay between dark matter and star formation also explains the cosmic timeline. The first stars, called population 3 stars, were giants, forming within the earliest halos a few 100 million years after the Big Bang. Their lives were short, but their deaths enriched the gas with heavier elements, setting the stage for later generations of stars and planets. Each step, from the collapse of pristine hydrogen to the building of complex galaxies, was guided by the gravitational wells of dark matter. Even the large-scale distribution of galaxies reflects this invisible architecture. Clusters of galaxies form where halos merge and grow, their gravity pulling in immense amounts of gas to fuel bursts of star formation. Vast voids, in contrast, are regions where dark matter is sparse, where few halos form and starlight remains scarce. The cosmic web, traced in galaxies, is really the web of dark matter itself, dictating where light will shine and where darkness will persist. It is remarkable to think that the stars we see, from the familiar ones in our own sky to the most distant galaxies caught in telescope images, owe their existence to something we cannot see. The night sky, dazzling with light, is in truth a gift of darkness. Each point of brilliance is perched in a gravitational basin carved by matter that refuses to glow, and without those basins, the sky might have been nearly blank. When you look up and trace the arc of the Milky Way, you are seeing more than stars. You are seeing the imprint of a halo that gathered gas across billions of years, cradling it long enough for stars to form, die, and form again. You are seeing a galaxy made possible by the silent presence of the unseen, by the dark matter that sculpts not just the shape of galaxies, but the very possibility of light itself. The universe was once imagined as a slowing breath, expanding outward from the Big Bang, only to be gradually tugged back by gravity. For much of the 20th century, astronomers expected that the cosmos might either collapse again in a great crunch or coast forever at an ever-diminishing pace. But in the late 1990 seconds, a discovery arrived that shattered that expectation. The universe was not slowing down, it was speeding up. Galaxies were accelerating away from one another, as though pushed by a force no one had foreseen. This force came to be called dark energy, and with its naming began one of the greatest mysteries in all of science. The evidence arose from the study of distant supernovae, specifically a kind known as type Ia. These explosions occur when a white dwarf star siphons matter from a companion until it reaches a critical mass and ignites in a runaway thermonuclear flame. Because the process happens at nearly the same mass each time, these supernovae shine with a predictable brightness. Astronomers can use them as cosmic yardsticks, comparing how bright they appear from Earth to determine how far away they truly are. By measuring both their distance and their redshift, the stretching of their light caused by cosmic expansion, astronomers hope to chart the history of the universe's growth. What they found was astonishing. The supernovae were dimmer than expected, meaning they were farther away than the standard models predicted. The universe had not just expanded, it had done so faster than gravity should have allowed. The conclusion was inescapable. Some unknown force was driving the acceleration, pushing galaxies apart with ever-increasing speed. Instead of a cosmos winding down, it was rushing outward, driven by an energy embedded in space itself. This revelation overturned our picture of the cosmos. For decades, dark matter had been the great unseen presence, the hidden weight holding galaxies together. But now something even more mysterious emerged, a force not of attraction but of repulsion, accounting for nearly 70% of the universe. While dark matter pulls, dark energy pushes. While dark matter clumps into halos and filaments, dark energy spreads smoothly everywhere, woven into the very fabric of space-time. The nature of dark energy remains elusive. Some suspect it is a cosmological constant, a property of space itself first suggested by Einstein and later abandoned when he thought the universe was static. Others imagine it as a dynamic field, changing over time, an invisible fluid filling the cosmos. Some even question whether our understanding of gravity is incomplete, and whether what we call dark energy is instead a symptom of deeper laws not yet uncovered. Each possibility reshapes our vision of the future. If dark energy is constant, the universe will expand forever, galaxies drifting apart until the night sky grows empty. If it strengthens, expansion could tear galaxies, stars, and atoms apart in a catastrophic Big Rip. If it weakens, gravity might one day reassert itself, slowing the expansion again. The mystery is not only about the fate of the universe, but about its present nature. Why should expansion accelerate now, billions of years after the Big Bang? Why does dark energy dominate the cosmos today, and not earlier or later? Astronomers call this the cosmic coincidence, a riddle with no satisfying answer. It is as if we are living at a special moment, balanced on the cusp between a universe of matter and a universe of energy, watching the handoff between what pulls and what pushes. And yet the evidence is overwhelming. The cosmic microwave background carries the imprint of acceleration. Galaxy surveys show its influence in the way large-scale structures have grown. Weak gravitational lensing hints at its presence in the distribution of matter. The supernovae that first revealed it continue to confirm the story. Everywhere we look, the universe insists it is expanding faster than it should. To contemplate dark energy is to stand at the edge of knowledge. It is not only unknown, it may be unknowable, at least in the terms we currently use. We name it for what it does. Dark, because it cannot be seen. Energy, because it drives motion. But these are placeholders more than explanations. The truth may lie in physics we have not yet discovered, in concepts as strange to us now as relativity or quantum mechanics once were. And yet, there is beauty in the mystery. The universe, far from being a finished story, is still unfolding with surprises. We are part of a cosmos not winding down but accelerating, rushing outward into a future we cannot yet imagine. Every star, every galaxy, every breath we take is carried along by a force we cannot see, embedded in the very emptiness between things. To live in such a universe is to live in wonder, held not only by gravity but also propelled by a darkness that drives the stars apart. Dark energy remains nameless at its core, a question disguised as a discovery. But it reminds us that even in our age of telescopes and satellites, of simulations and mathematics, the universe is not fully known. It still keeps secrets, still defies expectations, still reveals truths more startling than fiction. The night sky may look serene, but beneath that calm is a cosmos rushing ever faster into the unknown. When Einstein first formulated general relativity, he found himself unsettled by the conclusion it seemed to demand. The equations suggested a universe that could not remain static. Gravity, left unchecked, would cause the cosmos to collapse in on itself, to preserve a steady, eternal universe. The prevailing belief of the time, Einstein introduced a new term into his field equations, the cosmological constant. This constant acted as a kind of repulsive pressure, balancing gravity's attraction and holding the universe in equilibrium. It was not derived from observation, but from desire, a mathematical adjustment made to match the expectations of a motionless cosmos. Then came Edwin Hubble's discovery that galaxies were receding, that the universe was expanding, not fixed. Einstein abandoned his constant, calling it his biggest blunder, regretting that he had forced his equations to serve an assumption rather than letting them speak for themselves. For decades afterward, the cosmological constant was a footnote, a curiosity in the history of physics, unnecessary in a universe that seemed to be explained by expansion alone. And then, at the close of the 20th century, the universe surprised us again. The supernova measurements of the 1,990 seconds revealed not only expansion, but acceleration. Space was not merely stretching, it was stretching faster and faster, as if propelled by some unseen force. In that moment, Einstein's discarded constant returned, no longer a blunder, but perhaps the most natural explanation. A repulsive energy embedded in space itself, smooth and unchanging, pushing the universe outward in every direction. The cosmological constant is simple to describe and yet staggering to contemplate. It implies that empty space is not truly empty, but filled with energy, an energy whose density remains constant even as the universe grows. As more space comes into existence, more of this energy appears with it, fueling further acceleration. It is a feedback loop woven into the fabric of space-time. In this picture, the expansion of the universe is not slowing toward stillness, but rushing forward, driven by the very nature of the void. The implications are profound. If the cosmological constant truly governs cosmic acceleration, then the universe's fate is sealed. It will expand forever, galaxies receding beyond sight, stars burning out one by one, until all that remains is cold darkness and the whisper of radiation fading into silence. The sky itself will grow emptier as neighboring galaxies slip beyond the horizon, leaving each island of stars isolated in a vast sea of dark energy. The cosmological constant, born of a desire for permanence, ends by ensuring impermanence on the grandest scale. And yet, in its revival, there is a kind of elegance. Einstein's equations always allowed for such a term. It was only our assumptions that made it seem unnecessary. Now, as we try to grapple with the mystery of dark energy, the constant offers a straightforward possibility that acceleration is not the work of some exotic field, but simply the way the universe has always been written. What was once a mistake might be the truest expression of the cosmos. Still, questions linger. Why does the cosmological constant have the value it does? The energy it represents is unimaginably small compared to the scales of particle physics, yet large enough to dominate the fate of the universe. The discrepancy between theory and observation is so great that it stands as one of the most perplexing problems in modern science. The constant may be the simplest solution, but it is also one of the deepest riddles, a reminder that the void is not as empty as it seems. To imagine dark energy as the cosmological constant is to picture space-time itself imbued with a hidden tension, a fabric that does not merely stretch, but insists on stretching faster. Every moment, with every galaxy, the constant is at work, quiet and relentless, expanding the stage on which all things exist. It is not an added force, but a property of reality itself, woven into the background of existence. And so Einstein's blunder may yet be his triumph. The term he once regretted may turn out to be the key to understanding the greatest mystery of the cosmos. The cosmological constant is a reminder that even mistakes can be revelations waiting for their time, and that the universe often circles back to truths we thought we had outgrown. In the darkness between galaxies, in the emptiness that fills most of existence, something profound resides, shaping the destiny of everything that is. It is the quietest of forces, the most elusive of presences, and perhaps the most important constant of all. The discovery that the universe is accelerating forced physicists to ask not just how, but why. If the cosmological constant is the simplest explanation, it is also unsatisfying, a blunt answer that raises more questions than it resolves. And so, other theories have been imagined, each attempting to capture the elusive character of dark energy, each trying to explain why empty space behaves as though it carries a hidden force. None are proven, but each casts a different light on what the cosmos might be. One possibility is quintessence. Unlike the cosmological constant, which is fixed and unchanging, quintessence imagines dark energy as a dynamic field, evolving over time. It would be a kind of invisible substance permeating space, shifting in strength and behavior as the universe expands. If true, this would mean that cosmic acceleration is not a simple inevitability, but a story with chapters still unwritten. Quintessence could wax and wane, altering the pace of expansion, perhaps even reversing it one day. Some versions predict a slow fading of acceleration, others a future in which the push of dark energy grows stronger and tears everything apart. The appeal of quintessence is that it adds motion to the mystery, a living element rather than a static one. The difficulty is that no evidence yet shows dark energy to be changing, and until such variation is detected, quintessence remains only a graceful hypothesis. Another theory points not to a field, but to the energy of the vacuum itself. In quantum mechanics, even empty space is not truly empty. It seethes with virtual particles, flickering in and out of existence, leaving behind a baseline energy that cannot be erased. Physicists call this the zero-point energy, and it is tempting to link it to the acceleration of the universe. If the vacuum is filled with energy, might it not be the source of the repulsive pressure we call dark energy? The problem, however, is scale. When the vacuum energy is calculated from quantum theory, the result overshoots reality by an absurd margin. By a factor of 10 to the power of 120, the largest discrepancy between theory and observation in all of science. Reconciling this gulf is a challenge so deep it has been called the most embarrassing puzzle in physics. Still others argue that dark energy may not be energy at all, but a symptom of how we misunderstand gravity. Perhaps general relativity, though exquisite in its predictions, is incomplete at the largest scales. In this view, cosmic acceleration is not driven by a mysterious substance, but by gravity behaving differently across the vast reaches of space. Modified gravity theories attempt to adjust Einstein's equations, adding terms or new interactions that would naturally produce acceleration without invoking unseen energy. The attraction of this idea is that it shifts the problem from inventing a new cosmic ingredient to refining the laws we already use. But here, too, obstacles remain. General relativity has passed every test within galaxies and solar systems, and altering it without breaking those successes is a delicate, often impossible balance. These competing ideas reveal not only the depth of the mystery but also the limits of our knowledge. Quintessence offers dynamism, vacuum energy offers a physical mechanism, modified gravity offers a reformulation of the rules, yet none stands with unshakable evidence. Each struggles with unanswered questions, with predictions that either do not match what we see or are too subtle to measure with current instruments. Theories multiply, but proof eludes us. What unites them is the recognition that dark energy is not a detail to be tidied up, but a profound shift in our understanding of the universe. It forces us to question the emptiness between galaxies, the nature of space-time itself, and the fate of all things. Perhaps the answer is simple, and Einstein's constant is enough. Perhaps it is intricate, and a new field or a new law of gravity is required. For now, the evidence remains mute, the universe accelerating without explanation, the silence of the data as eloquent as any theory. To sit with this mystery is to acknowledge the humility of our position. We live in a cosmos dominated by forces we cannot yet name, where light and matter are the exceptions rather than the rule, where emptiness itself drives the expansion of everything. Our theories are sketches, our models provisional, our understanding incomplete. And yet, in the act of asking, of imagining quintessence or vacuum energy or new laws of gravity, we come closer to the truth, feeling along the edges of the unknown. Perhaps one day the mystery will yield. Perhaps new observations will reveal a change in dark energy over time, or a subtle deviation in gravity's pull, or a deeper link between quantum fields and the structure of space. Or perhaps it will remain, a reminder that the universe is not obliged to explain itself, that wonder is as much a part of science as certainty. For now, dark energy sits at the heart of the cosmos, like a question too large for any single answer, a force both everywhere and elusive, shaping not only the expansion of the universe, but also the horizons of human thought. When Edwin Hubble turned his telescope to the distant galaxies of the 1,920 seconds, he found something that would transform our understanding of the universe forever. Their light was stretched, shifted toward the red end of the spectrum, not just in one case, but in all directions. The farther away a galaxy was, the more its light was redshifted, as though space itself were carrying it from us. Hubble's measurements revealed that the universe was expanding, not static as long assumed. The cosmos was not a fixed stage on which galaxies performed, but an ever-stretching fabric in which the galaxies themselves were carried apart. This discovery shattered the idea of a timeless universe and gave birth to the concept of the Big Bang. If galaxies are receding today, then in the past they must have been closer together. Wind the film of cosmic history backward, and everything converges to a single, dense origin. For the first time, the universe had a beginning. Expansion was not a subtle detail, but the central truth of cosmic existence, woven into every ray of starlight we see. For decades, astronomers assumed this expansion must be slowing. Gravity, after all, is universal, and the combined mass of all stars, gas, and dark matter should tug at the fabric of space, resisting the outward rush. The great question of the 20th century was whether the universe had enough matter to eventually halt and reverse expansion, collapsing in a big crunch, or whether it would expand forever, coasting ever more slowly toward stillness. Cosmology was framed as a choice between these fates, the answers hinging on the unseen weight of the cosmos. But at the end of the century, the sky revealed a twist. Observations of distant type Ia supernovae showed that galaxies were not only receding, but receding faster than expected. The expansion was accelerating. Instead of being slowed by gravity, the universe was being pushed outward by something new, something repulsive. This was the birth of dark energy in our vocabulary, a force not of collapse but of acceleration, hidden within the very emptiness of space. The revelation was startling. The universe would not merely expand forever. It would do so at an ever-increasing rate. Over time, galaxies beyond our local group will slip beyond the cosmic horizon, their light stretched until it can no longer reach us. The night sky, billions of years from now, will empty as the distant stars vanish from view, leaving only the dim glow of our own galactic neighborhood. Acceleration has rewritten the universe's destiny, replacing the possibility of collapse with a future of isolation and silence. Yet, even as the fate of the cosmos seems clearer, the cause remains obscure. What is driving the acceleration? A cosmological constant embedded in space-time itself, a dynamic field evolving through cosmic history, a flaw in our understanding of gravity? We do not know. The expansion we can measure with exquisite precision, but the reason behind it remains hidden. We see the effect but not the engine, the outcome but not the cause. Still, there is a certain wonder in knowing we live in such a universe. Expansion is not only a fact of cosmic history, but a fact of our everyday existence. The very atoms of our bodies, the starlight that reaches our eyes, the galaxies that glitter overhead, all are participants in this grand stretching of space. The universe breathes outward, and we are carried with it. Hubble's discovery showed us that the cosmos is alive with motion, not fixed but flowing. The revelation of acceleration deepened the mystery, turning what once seemed a simple trajectory into a question without end. We live in the middle of that story, suspended between what we know and what we cannot yet explain. And in that mystery, the universe becomes not smaller, but larger, inviting us to wonder not only where it came from, but where it is going, and what hidden forces are guiding it into the future. The fate of the universe is written not in the stars themselves, but in the unseen hand that drives them apart. For most of history, people imagined the cosmos as eternal, a stage set once and for all. Then came the revelation of expansion, and later, the deeper shock of acceleration. Now, instead of certainty, we are left with possibilities, branching paths that depend on the true nature of dark energy, the mysterious force propelling the universe outward. Each path is profound, each outcome humbling, and all are bound by the same question: how does the story end? If dark energy is the cosmological constant, a steady pressure woven into space-time, then the universe will expand forever at an ever-quickening pace. Over billions of years, galaxies beyond our local group will drift past the cosmic horizon, their light stretched into invisibility. One by one, the great clusters will disappear from view, leaving only the dim glow of our nearest neighbors. Stars will burn through their fuel, fading into white dwarfs, neutron stars, and black holes. Even those remnants will eventually cool and decay, leaving a cosmos empty of light. In this scenario, called heat death, the universe ends not in fire but in silence, a vast cold sea of expanding space where nothing new can form. Yet the future could be more violent. If dark energy is not constant but grows stronger over time, the acceleration could become catastrophic. Galaxies would not merely recede, they would be torn apart. Stars bound in galaxies would separate, planets would drift from their suns, and eventually even atoms themselves would be ripped as the expansion overcame the strongest forces of nature. This is the vision known as the Big Rip, a universe unraveling under the weight of its own acceleration, everything stretched into nothingness in a final moment of dissolution. There is also the possibility of endless but gentler expansion, where dark energy evolves but never overwhelms. In this case, galaxies continue to recede, but local structures, clusters, stars, planets, remain intact. The night sky slowly empties, but the bonds of gravity preserve pockets of light for trillions of years. Stars are born, burn, and die on timescales almost beyond imagination, until at last the raw material for new stars is exhausted. What follows is a slow dimming, a gradual fading into darkness, as the embers of creation wink out across a universe that never ends, but also never renews. Each of these scenarios is governed by the same unknown: the exact nature of dark energy, constant or changing, gentle or fierce, determines the path the cosmos will take. Our instruments measure expansion today with exquisite precision, but the long arc of the future remains hidden, folded inside a force we cannot yet define. It is as though the universe has shown us the beginning of a sentence, but left the ending unwritten. And yet, in contemplating these endings, there is more than dread. There is also wonder. To realize that the universe has a fate at all is to understand our place within a story larger than time itself. The stars we see are not eternal, but temporary lights in a cosmos whose future may be silence or rupture. We exist in a fleeting window, when the universe is full of galaxies and light, when the night sky is crowded with brilliance. Future observers, if any remain, may not see what we see. They may look into the dark and find only emptiness, unaware that once the universe was radiant. To live now is to live in a rare chapter of cosmic history, to witness both the beauty of galaxies and the mystery of the force that is pulling them apart. Whether the universe ends in heat death, in rip, or in endless expansion, the fact remains that its destiny is bound to the invisible, to dark energy's secret nature. Our role is to ask, to measure, to wonder, knowing that the answers lie not in our control but in the fabric of space-time itself. The fate of everything is a question larger than any one age of science can solve. It is a horizon beyond our reach, but not beyond our imagination. And perhaps that is what makes it so haunting. The realization that the universe is not only vast in space, but also in time, and that the future awaiting it may be stranger and lonelier than we can yet conceive. When we look into the night sky, we are not just seeing stars as they are now. We are peering into a history written in light. The oldest of all that light is the cosmic microwave background, the faint afterglow of the Big Bang, released when the universe was only about 380,000 years old. It is a whisper from an era when matter and radiation first parted ways, when the cosmos cooled enough for atoms to form and light to stream freely through space. That glow, stretched and cooled by billions of years of expansion, still surrounds us today, arriving from every direction, nearly uniform, but not perfectly so. Within its tiny variations lie the fingerprints of dark energy. The microwave background is often imagined as a smooth curtain, but in truth it is patterned with subtle ripples, slight temperature differences that mark the seeds of cosmic structure. These ripples tell us how matter clumped, how sound waves rolled through the early plasma, and how gravity tugged on every particle. By studying them with exquisite precision, cosmologists can reconstruct the conditions of the young universe and test how it evolved. It is here, in this ancient tapestry, that the presence of dark energy makes itself felt, not directly, but through its influence on the growth of structure and the geometry of spacetime. When photons of the microwave background began their journey, the universe was tiny compared to today, and dark energy's influence was negligible. Matter and radiation dominated, pulling and shaping the expansion. But as the universe grew, the balance shifted. Billions of years later, dark energy rose to prominence, accelerating expansion and altering the distance those ancient photons traveled before reaching us. In this way, the microwave background carries an imprint of dark energy, written not in its origin, but in its journey. The geometry of the universe reveals itself in the size of the ripples imprinted on the microwave background. These ripples, known as acoustic peaks, have a characteristic scale determined by the speed of sound in the early plasma and the age of the universe when light broke free. If the cosmos were curved differently, those peaks would appear stretched or compressed on the sky. By comparing what theory predicts with what satellites like WMAP and Planck have measured, scientists can tell that the universe is flat to remarkable precision. But flatness alone is not the whole story. To fit the data, something like dark energy must be included, a component that ensures the cosmic expansion matches the observed geometry. Without it, the peaks do not align. There are also more subtle clues, found in the way the microwave background's photons have been tugged by gravity on their way to us. As they pass through clusters of galaxies and cosmic filaments, their paths bend and their energy shifts, a process called lensing and the integrated Sachs-Wolf effect. In a universe without dark energy, these signatures would appear differently. The fact that we see them as we do is further confirmation that acceleration has been sculpting the cosmos for billions of years, leaving a faint but undeniable echo in the oldest light. What makes this remarkable is not only the detection of dark energy's presence, but the precision with which it is measured. The cosmic microwave background is mapped to millionths of a degree, every pixel a record of conditions from nearly 14 billion years ago. The data, when combined with surveys of galaxies and supernovae, forms a consistent picture. About 70% of the energy of the universe is this mysterious, repulsive force. The numbers converge as though the cosmos itself were whispering the same truth through multiple channels, each reinforcing the other. And yet, as precise as the measurements are, they do not explain what dark energy is. The microwave background confirms its necessity, but not its identity. It tells us the amount, the influence, the imprint, but not the nature. In that sense, the background light is both a revelation and a riddle, a message from the dawn of time that we can translate into numbers, but not into meaning. Still, there is a quiet wonder in knowing that when you tune a radio to static, some of that hiss is this ancient light, stretched across the ages, carrying within it the story of everything that would follow. Embedded in that faint glow is the evidence that space itself would one day accelerate, that galaxies would drift apart faster and faster, that the destiny of the cosmos would be shaped by something invisible. To study the microwave background is to look not only backward to the first light, but forward to the fate of everything, all encoded in a sky that glows, ever so faintly, with the memory of beginnings. The universe is a vast puzzle, and every new generation of telescopes is another set of eyes straining to read its pieces. For dark matter and dark energy, the tools of the future are not just sharper mirrors or bigger domes, but entire systems designed to map the invisible. We have learned that the cosmos is dominated by what we cannot see, and so the instruments now being built are aimed not only at stars and galaxies, but at the subtle patterns of gravity, geometry, and light that reveal the unseen. One of the most ambitious of these is the Euclid mission, launched by the European Space Agency. Euclid is designed to chart the geometry of the universe on the largest scales, tracing how galaxies cluster and how cosmic structures have grown over billions of years. By measuring both weak gravitational lensing, the tiny distortions in galaxy shapes caused by invisible mass, and the large-scale distribution of galaxies, Euclid will map dark matter's scaffolding and test the influence of dark energy on cosmic expansion. In its wide field of view, millions of galaxies will be captured not as isolated jewels, but as points in a grand structure, a three-dimensional atlas of the hidden universe. On Earth, another eye prepares to open, the Vera Rubin Observatory in Chile. Its wide-field survey will be like nothing attempted before, imaging the entire southern sky every few nights. Over 10 years, it will build a movie of the heavens, capturing how galaxies shift, how stars flare, how faint objects reveal themselves. For dark energy, the Rubin Observatory will measure billions of galaxies across cosmic time, tracing their distribution to detect the subtle signature of acceleration. For dark matter, it will watch how gravitational lensing bends light on small scales, revealing the halos that cradle galaxies. The project is more than a telescope. It is a time machine, showing how the universe evolves frame by frame. Then there is the James Webb Space Telescope, already staring deep into the earliest epochs of cosmic history. Webb's infrared vision can pierce the veil of dust and look farther back than Hubble ever could, to the time when the first galaxies formed. In this way, Webb complements the surveys of Euclid and Rubin, where they map the broad strokes of cosmic structure. Webb zooms in on the details, showing how galaxies lighted by early stars emerged within dark matter halos. Its view connects the smallest beginnings to the largest frameworks, linking the story of structure to the mystery of expansion. Meanwhile, the Dark Energy Spectroscopic Instrument, or DESI, sits on a mountain in Arizona, designed to measure redshifts for tens of millions of galaxies. With 5,000 tiny robots positioning optical fibers each night, DESI can capture the spectra of galaxies across vast swaths of sky. Each spectrum reveals a galaxy's distance, and together they form a three-dimensional map of cosmic structure stretching across most of cosmic history. By measuring the patterns of galaxy clustering, DESI seeks the imprint of baryon acoustic oscillations, the frozen echoes of sound waves from the early universe. These ripples act as a cosmic ruler, and by charting them at different times, DESI will measure how expansion has changed, testing the fingerprints of dark energy with precision. Together, these projects form a symphony of observation, each instrument tuned to a different aspect of the same enigma. Euclid will trace the cosmic web with unprecedented breadth. Rubin will watch the living sky evolve. Webb will peer into the dawn of structure. Desi will carve the history of expansion into a detailed map. Each will contribute a piece, and together they will constrain not just how much dark matter and dark energy exist, but what they are and how they behave. Yet, even as they promise clarity, they also remind us that the mystery may deepen. Greater precision can sometimes bring sharper paradoxes. The more finely we measure dark energy, the more peculiar its constancy may seem. The more completely we map dark matter, the more elusive its particle nature may appear. These telescopes and surveys are not only searchlights, but magnifying glasses, showing us both the beauty of the structure and the strangeness of the unknown. To imagine the future is to picture the night sky not just as a canvas of stars, but as a vast data set. Every photon captured, every distortion recorded, every shift catalogued. The universe is preparing to reveal itself in patterns too subtle for human eyes alone, requiring the patience of machines and the persistence of decades. When the images come, they will not only be beautiful but also unsettling, carrying answers about why galaxies exist, why the cosmos accelerates, and what destiny awaits it all. In the end, the surveys and telescopes are not separate endeavors but chapters of the same story, a story written in light and shadow. They are our instruments of curiosity, our means of listening to the silence of dark matter and the whisper of dark energy. When their work is done, we may not hold the final answer, but we will have come closer, tracing the outlines of mysteries that will shape not only our understanding of the cosmos, but also the way we imagine our place within it. To say that most of the universe is invisible is to admit something astonishing about our place within it. The stars that fill the night sky, the galaxies that swirl across the dark, even the dust and gas clouds that stretch between them. These make up less than 5% of all that exists. The rest is hidden, divided between dark matter and dark energy, entities we cannot see or touch, known only by their effects. In the vast accounting of the cosmos, the luminous is the exception, not the rule, and we ourselves, made of ordinary atoms, are born of the rarest fraction of the whole. There is a kind of humility in this realization. For centuries, humanity has placed itself at the center of the story. First, literally, as the earth was thought to sit at the center of the heavens, and later, figuratively, as the creatures who could unlock the universe with reason. But the discovery of the unseen undermines both positions. We are not at the center, and we are not even composed of the main ingredients. We are a marginal note in the cosmic ledger, small and improbable. And yet, it is precisely from that marginality that our wonder arises, the ability to contemplate what lies beyond us. Dark matter and dark energy are not merely scientific curiosities. They are philosophical provocations. They remind us that what is real is not always visible, that existence exceeds perception, and that truth often dwells beyond the reach of certainty. They force us to live with unanswered questions, to embrace a universe that withholds as much as it reveals. In this way, they mirror the human condition itself, our search for meaning, our awareness of limits, our restless desire to reach beyond them. The existence of the unseen also deepens the mystery of knowledge itself. Science is often imagined as a march toward clarity, a steady illumination of what was once dark. Yet the discovery of dark matter and dark energy expands the darkness rather than reduces it, revealing that what we thought was the whole is only a fraction. To measure the unknown with exquisite precision is not to solve it, but to better articulate its strangeness. The more we learn, the more mysterious the cosmos becomes. And still, there is beauty in this tension. To live in a universe filled with the unseen is to live in a universe that inspires humility, but also wonder. The stars we see are framed by what we cannot see. The galaxies we measure are shaped by what we cannot explain. We are participants in a cosmos that is larger than comprehension, and that largeness is not a defeat, but a gift. It keeps us asking, it keeps us imagining, It keeps us reaching. There is also an existential undertone to these discoveries. If most of the universe is invisible, then the familiar world is not the norm but the anomaly. What does it mean to be made of the rarest substance, to live in the brief epoch when stars shine, to ask questions about a cosmos that will one day be silent? The knowledge places us in a fragile position, but it also grants us perspective. We are fleeting, but we are aware. We are small, but we are able to look across billions of years and billions of light years, perceiving patterns that transcend us. In this sense, the mystery of dark matter and dark energy does not diminish us but enlarges us. To know that we do not know, to stand before the vastness of the unmeasured, is itself a profound act. The universe is not obliged to make sense to us, and yet it offers clues, curves of galaxies, arcs of light, faint ripples in ancient radiation. It gives us enough to wonder, enough to keep searching, enough to glimpse the outlines of mysteries we may never fully solve. Perhaps that is the final philosophical gift of the dark universe. It teaches us that not all questions end in answers, and not all mysteries are meant to be solved. Some exist to remind us of our limits, and through them, of our place. To live in such a universe is to live in awe, to see the night sky not only as a scatter of stars, but as the surface of something immeasurable. The darkness is not emptiness but fullness, not absence but presence, not a void but a vast reminder that the story of existence is greater than what shines. 100 truths gathered, not in brightness, but in shadow. They began with the realization that most of the cosmos is invisible, that what we see in stars and galaxies is only a fraction of what exists. From that first unveiling came a journey through galaxy rotations too swift for visible matter alone, through the scaffolding of dark filaments holding galaxies like dew on a web, through light bent and split by unseen hands. Each fact was not a conclusion, but a doorway, opening into the next. We followed Vera Rubin, watching stars spin too fast to be bound by what they showed. We traced the arcs of gravitational lensing, where galaxies far behind others curved into halos of light that betrayed hidden mass. We watched clusters of galaxies, their luminous gas left behind while invisible matter passed through untouched, the bullet cluster marking its path like smoke after a fire. We stepped into underground chambers where tanks of liquid xenon waited for a whisper of particles, and into imaginations where faint stars, rogue planets, or primordial black holes offered themselves as candidates only to falter before the evidence. We turned back to the dawn, when the cosmic microwave background still hummed with ripples of plasma, encoding the presence of dark matter before stars were born. We charted maps drawn not in starlight but in distortions of geometry, vast surveys that revealed the invisible as patterns, structures, webs across billions of years. We stood at the edge of galaxy halos, realizing that every spiral, every disk of stars, floats in an ocean of gravity it cannot reveal. And we saw how these halos became the cradles of stars, the necessary wombs for creation, without which galaxies would not form and light would not shine. Then the story turned, from the pull of dark matter to the push of dark energy, from Hubble's discovery that galaxies recede to the later shock that they accelerate. We learned that emptiness itself is alive. Einstein's abandoned constant returned, perhaps not a blunder but a truth too soon set aside. Other visions, quintessence, vacuum energy, altered laws of gravity, were offered, but none proved, each one a reminder that our grasp is incomplete. From these came the contemplation of destiny, a slow heat death where stars fade into silence, a catastrophic rip where space tears everything apart, or a future of endless expansion, where galaxies vanish one by one beyond the horizon. The evidence of this acceleration is not written in words, but in light. It lies in the dimming of supernovae, in the ripples of the microwave background, in the clustering of galaxies measured by spectrographs and surveys. It is etched into the sky, waiting for Euclid, Rubin, Webb, DESI, and other instruments to refine the story, to measure the silence with greater precision. Each telescope is a hand stretched into darkness, each survey a reminder that to map the universe is to chart not only light, but the invisible scaffolding that supports it. And finally, beneath the science, beneath the measurements, there remains the philosophy. What does it mean that the majority of the cosmos is invisible and unexplained? It means that humility is demanded of us, that our knowledge is partial, provisional, incomplete. It means that mystery is not failure, but the very texture of existence, something to sit with, to wonder at, to allow. It means that even if we never hold the final answers, we are still held by the beauty of the questions themselves. 100 truths, each one pointing not to certainty, but to wonder. They remind us that the stars in the sky are not the whole story, that the glow we see rides on a sea of shadow, that existence is vaster than perception. And so, in the end, the lesson is not that we are lost in mystery, but that mystery itself is home. To lie back beneath the night sky is to rest within it, to breathe with it, to accept that not all things must be solved. Some can simply be admired, the way one admires the outline of a mountain in dusk, or the curve of a galaxy drifting in silence. The darkness is not absence, but presence, not emptiness, but fullness. And in knowing this, we can rest.